This episode is supported by CuriosityStream. There's been a lot of talk lately about putting humans on Mars, and even colonizing the Red Planet. Is this even possible? And what would that settlement actually look like? Mars is getting a lot of attention. NASA's new budget mandates a 25-year timescale for putting astronauts in orbit around Mars. That's exciting. But Elon Musk soon followed with a rather more audacious announcement. SpaceX plans a spacecraft capable of transporting 100 people at a time to Mars. Not to visit, but to settle. And it may be done in as little as 10 years. The ultimate aim is for a completely self-sustaining extraterrestrial colony of 1 million people within several decades. That's some ambition. Here's the lowdown. Musk announced this in an hour-long presentation that was almost entirely about the vehicle. First step, a spaceship is launched into orbit by a rocket booster. The booster then returns to its launch pad and is loaded with a giant fuel tank. It relaunches and delivers to the orbiting spaceship enough fuel for the 4-month journey to Mars. This is only feasible because of the reusability of the components. That means many return trips to Mars, but it also allows the booster to carry the spaceship and the fuel in separate launches. As a result, the spaceship itself can have a much bigger payload, translating to 100 passengers, rather than, say, the 4 astronauts of NASA's proposed Orion module. Now, I could go into all of the details, but honestly, you should just listen to or read Musk's announcement. Links below. Is the vehicle actually possible? Sure, probably. Whether 10 years is remotely feasible is another matter. That's the lower limit in the case that, as Musk puts it, things go super well. The plausibility of this may be governed by whether a Martian colony could really work. Musk says almost nothing about that, so let's get into that today. The vision is for a completely self-sufficient settlement. Anything less would defeat the main point, to be a safeguard against our extinction. It needs to be able to thrive, even if Earth is lost. It needs to mine, farm, process, and manufacture everything it needs. It also needs to be a place that people might actually want to live. What would that look like? The initial habitats are going to be simple, and in fact the first landers probably need to bring habitats with them. That 450-ton cargo capacity of the spaceship will help there. These may be inflatable modular structures similar to those proposed by Mars 1, or like the Bigelow Expandable Activity Module, BEAM, that's already in use on the International Space Station. An important advantage of prefabricating habitats on Earth is that you can use advanced materials with better radiation shielding. Mars's thin atmosphere and lack of magnetic field make shielding critical, especially for a permanent settlement. However, to protect against high-energy cosmic rays and solar outbursts, and from the micrometeorites that also pass easily through Mars's thin atmosphere, we really just need a very thick roof. That means either living underground or building dense shelters from local material. Becoming Martian mole people may be the way to go. For one thing, Mars does have lava tubes that could be populated. But with the advent of large-scale 3D printing, it's possible to build these structures on a planet's surface. NASA's 3D Printed Habitat Challenge produced some incredible concepts. Some proposed harvesting the abundant iron and silica from the Martian soil to print a variety of structures. The winner, however, was pretty unique. A 3D printed dome of ice, under which pressurized habitats could be built. That's right, we may end up living in Martian igloos. The water we'd need for that is abundant as ice frozen within the Martian surface. That same water is really what makes this whole endeavor possible. We need it to drink, to grow food, but H2O may also be the best supply of oxygen for, well, breathing. Mars' atmosphere is 96% CO2 and the rest equal parts nitrogen and argon. But scrubbed of CO2, that nitrogen-argon mix makes a breathable buffer gas that we top up with 20% oxygen. It's been tested on mice and crickets, so I guess we're good to go. Growing plants for food requires water and air, but also light. So we need either transparent greenhouse enclosures or artificially illuminated hydroponic farms. Modern hydroponic farms are proving vastly more productive and require far less water than their dirt-based equivalents, so that's a promising direction. Especially because it's hard to protect against radiation with a transparent roof. Also, those plants will help with oxygen production. Of course, all of this requires energy, and this may be the simplest part. Giant solar arrays stretching across the Martian surface are the obvious answer. The one outstanding technical issue is the gravity. Mars's gravity is 0.38 times that of Earth. We know that astronauts lose around 2% of bone mass per month in zero-G. It's surely less on the surface of Mars, but we just don't know how serious this would be after many years. To build a sustainable, multi-generational civilization, it may be necessary to simulate Earth gravity. This is possible using a centrifuge, a rotating ring that results in the feeling of an outward force, a centrifugal force, with respect to the ring. This has been proposed for artificial gravity on long-term space missions, but it's also possible on a planetary surface. It would still involve a large rotating ring, but with a sloped, slightly curved outer wall so that the centrifugal and gravitational accelerations work together to give you the right direction of down on that surface. To avoid annoying daily centrifuge visits, perhaps in the long term, we'll build entire centrifuge cities, levitating on superconducting magnetic rails and rotating once every few minutes. On the other hand, watching the entire sky rotate that fast may be as bad for the stomach as 0.38 G is for the bones. We may want to keep that thick roof of rock or ice. Martian cities are technically doable, and people will certainly want to go. 200,000 signed up for the Mars One program. Really, the feasibility of this is more a question of economics. Once we lose the inexorable driving force that is Elon Musk, a Martian settlement will have to be entirely self-sufficient or economically productive enough to justify continued life support from Earth. Whether that can happen quickly enough is the real question. A lot of what we learn about living on Mars will work elsewhere in the solar system too. In fact, the proposed spacecraft is meant to be a general-purpose solar system explorer. Where would you go? Mars will be fun, but we're really holding out for those Venusian cloud cities here at Spacetime. We want to thank CuriosityStream for supporting this episode of Spacetime. Go to curiositystream.com/spacetime. CuriosityStream is a membership service that streams non-fiction documentaries and series from some of the world's leading filmmakers. There are a variety of topics like science, nature, history, and many others, plus interviews, lectures, and original exclusive documentaries from people like Stephen Hawking and Jason Silver. CuriosityStream is available on many platforms like Roku, Android, iOS, Chromecast, Amazon Fire, Amazon Kindle, and Apple TV. Go to curiositystream.com/spacetime for more information and a membership trial. Be sure to help us out by using the promo code SPACETIME. Hey guys, Vsauce is doing an amazing series on Mars exploration and colonization. Jake at Vsauce 3 and I have chatted a lot about what humanity's first experiences will be like when we go to Mars. Jake's take on this question will be coming out real soon. The link will be right here when it does. Keep your eye out for it. Last week, we talked about the incredible, if speculative, possibility that primordial black holes formed in the insanely dense conditions right after the Big Bang, and that these might still be around today. I want to address two big questions that you had in the comments. Several of you asked how to tell the difference between a primordial black hole and a black hole formed when a very massive star ends its life. Well, actually, a black hole is a black hole is a black hole regardless of how it formed, or what it formed from. Even a black hole made entirely from light, a Kugelblitz, is the same thing as a black hole formed from regular matter. Black holes exhibit only three properties: mass, electric charge, and spin. You can learn something about the formation of a black hole from those properties. Mass is one way to identify a primordial black hole from a stellar black hole. A star's core needs to be more massive than around 3 times the mass of the Sun in order to collapse into a black hole. Otherwise it becomes a neutron star. However, primordial black holes don't form from stars and so aren't subject to this restriction. They could in principle be any mass. Also, if we find many PBHs spread through the galaxy, and even outside the galaxy, their distribution may tell us that it was impossible for them to have been produced by massive stars, which are rare as far as stars go. A few of you also asked whether the supermassive black holes that we find at the centers of galaxies could be primordial black holes. Well, the answer is yes, but it's really hard to say for sure. Those supermassive black holes started as much smaller seed black holes. Those seeds may have been from the very first generation of supernovae near the beginning of the universe. However, they may also have been from PBHs from an even earlier time. Some scientists like that idea because we see some pretty gigantic supermassive black holes in the early universe, and it's quite tricky to explain how they got that big if they grew from only stellar mass black holes. Very large primordial black holes may help explain this, but there's no evidence for this idea.